In this video, I'm going to talk about sensitivity and specificity calculations in the context of conducting something like a logistic regression, which can be considered a good addition to reporting results relevant to classification accuracy. And so I'll start with sensitivity first. So sensitivity is the proportion of cases classified accurately by the model to possess or have the characteristic of interest. So that's the key element of sensitivity, is that the cases possess the characteristic that you're interested in. And in this example, we're interested in predicting people who have dyslexia. So that's, you could frame sensitivity in that context. Who has dyslexia, and is the model predicting who does? So for example, the data might be coded 0 and 1 in a dichotomous dependent variable. And in this example, 0 was not dyslexic and 1 was dyslexic. The key thing, though, is that the number 1 is known to me, the researcher, to possess the characteristic of interest. It's also known as the true positive rate. So again, going back to the idea that I'm trying to predict who has dyslexia on the basis of handedness, and that's a positive prediction, if you will, if the model can actually classify or identify somebody who has dyslexia on the basis of handedness. That's a positive prediction or a positive classification. That's sensitivity. So before I go to specificity, I'm actually going to show you an example in SPSS output where you get sensitivity and where you can calculate it. And this goes back to the logistic regression, the binary logistic regression, using handedness to predict dyslexia. And this was the null model where there was 96% classification accuracy based only on the descriptive statistics, which is not impressive in this case because the vast majority of people didn't have dyslexia. So it's easy to make a prediction. You could just say people probably don't have dyslexia, and you'll be accurate in a large percentage of cases. When we went to the model that included handedness as a predictor, the correct classification didn't increase. It stayed at 96%. And that was true even though Cox and Snell was 0.048. So about 5% of the variance was accounted for by the inclusion of handedness in the model. That wasn't enough, though, to actually increase the prediction, the classification table. So now if I break this down into sensitivity and specificity, so if we recall that sensitivity is the proportion of cases accurately classified to possess the characteristic of interest. So in this case here, that would be the proportion predicted to have dyslexia. So I'm in this column here, predicted yes. And what proportion were accurately predicted to possess dyslexia? It was actually 0. All 10 of the dyslexics in the sample were identified incorrectly to not have dyslexia. So in this case here, sensitivity was actually 0. Once you've looked at sensitivity, you should always also look at specificity, because you can get a very skewed perception of how good your model is if you're only looking at one. So specificity is the proportion of cases classified accurately to not possess the characteristic of interest. So in this example, that would be not having dyslexia, which is a very large percentage of people in this data file. It's about 95%. And so as an example, you might code your data 0, which is the absence of the characteristic, so that's the not having dyslexia, and 1, which is the presence of the characteristic, which is dyslexia. Now again, just like sensitivity, specificity also has another term that I think is a little more insightful, which is the true negative rate. Negative implying not possessing the characteristic of interest. So if we go back to the observations of predicted and observed frequencies, we can see that the upper row here is relevant to specificity. We can see that the number of people who do not have dyslexia is equal to 240 if I add this cell to this cell, because 240 plus 0 is equal to 240. In contrast to sensitivity, where I use this value to divide from the sum of these two cells, with respect to specificity, I would divide this cell by the sum of these two cells, because this is no and no, the absence of the characteristic of interest. No dyslexia. So in this case here, 240 plus 0 is equal to 240. And then if I divide 240 by 240, I get 1. And that suggests the specificity is extremely high. The model is very accurate at predicting who doesn't have dyslexia. But it's also very poor at predicting who doesn't have dyslexia. So when you take your sensitivity and your specificity together, this model is not impressive. And that is essentially consistent with the notion that the model only had a Cox-and-Snell R-squared of 0.048%, which implies that about 5% of the variance, if you will, was accounted for in the dependent variable, which wasn't enough to push one correct classification of dyslexia into this cell. It just wasn't quite strong enough. Maybe if Cox-and-Snell was closer to 10%, maybe one case would slip into this cell, and then my sensitivity statistic would look better. In that case there, if I even just had one person here, I could then divide 1 by 10, and then I would have sensitivity of 0.10, which still isn't great, but it's still something that's better than 0. Now let me show you another example where the numbers are a little more interesting, where not both sensitivity and specificity are actually 0. The example is absenteeism and turnover, and I'm only going to look at one predictor variable, which is the employee's absenteeism levels across a year of work and whether that person ended up leaving the job or not. So let me just do that logistic regression quickly here. So absenteeism in my covariate box and turnover in the dependent box. Classification plots, Hosmer, Lemeshow, goodness of fit, and that should be enough. I really just want the key table with the observed and predicted values. We can see the sample size is 226, and with the null model there was actually 50% correct classification, which is bang on in the middle. And then when I go to the actual model that includes a predictor variable, it has increased to 57.5%, which corresponds only to 4.4% of the variance, and the Hosmer and Lemeshow statistic is actually suggesting that it's not even strong enough to be significant. This p-value, recall, is the opposite when you interpret it with respect to significance. But I can still calculate sensitivity and specificity here, and it's a little bit more interesting. So in this case here, I'm trying to predict who leaves the company. And so in that context, sensitivity, as I show here, where 1 is the value of interest, and that's a leaver. So a leaver and a leaver, 42 cases were identified as a leaver and were in fact a leaver. So if I want to calculate sensitivity, I would sum this value and this value, so 71 plus 42 equals 113, and then I divide 42. 42 divided by 113 gives me 0.372 for my sensitivity value. So that's the correct classification of the characteristic of interest, which is the levers. Now, when it comes to specificity, which is the correct classification of the cases that are not of interest in the context of I'm trying to predicting levers, I've got stayers. And in this case, there are 88 cases that were stayers, and they were predicted accurately to be stayers. So again, 88 plus 25 happens to equal 113, and I divide this cell value by 113 to get the specificity. 88 divided by 113 equals 0.779, which is a very good value. So I've actually got sensitivity of 0.37 and specificity of 0.78, and these values are fairly good. Now the Hosmer and Lemeshow statistic wasn't suggesting a statistically significant Cox-and-Snell R-squared value, but the absenteeism value in the equation and with respect to the unstandardized beta weight was actually statistically significant in this case. So there is a bit of a disconnect between the Hosmer-Lemeshow test and the unstandardized beta weight in this case. Now that's a separate issue. The main point is calculating sensitivity and specificity, and these two examples are really quite different, mostly because the handedness and dyslexia example is based on a relatively low proportion of cases that even have the characteristic of interest, and it was very tough to even predict that even just one case. Whereas in this instance, stayers and leavers, there was a really healthy mix of both of them in this sample of data.